In today's video, we're going to do a summary about the log graph. So first, let me write down the equation. No, write down the function again. Y equals log base a of x. Okay. First, let me talk about the restriction on a and x. Okay. If you look the video about exam correction, you probably know there is restriction on the base and x. So remember, first, for the base, this base must be bigger than 0 and cannot be 1. Okay? And for x, x must be bigger than 0. Okay, so this is the restriction for log. So now we know for the domain of this log function, y equals log base a of x, x must be bigger than 0. Okay? How about the range? Okay, the range, we'll talk about the y, so the whole thing, log base a of x. We can actually see the range on the graph. Okay, you can see the y-axis. Can y be a positive number? Y can be a positive number, right? Because there is a corresponding point. Okay. Or y can be 0, right? Or y can be negative number. So what does that mean? That means our range is actually the set of all real number. Okay, so the first thing about the log function is we know the domain and range. The second thing, we will talk about the common features. Okay, we have actually two special cases. One is a is bigger than 1, and the other one is a is in between 0 and 1. They both have the common features. But let me just talk about the first case, okay? A bigger than 1. So the first common feature is the graph cuts the x-axis at one point, okay? You can see the graph. The graph cuts the x-axis at this point, right? So what are the coordinates of the point then? We know that all points, if the lines on x-axis, its y coordinate must be 0. So what does that mean? That means we can substitute if y equals 0. So we get 0 equals log base a of x. Okay, so what is x? Okay, can we write in terms of exponential form? We can write as a to the power of 0 equals x. So x equals a to the power of 0. So a to the power of 0 is what? Is 1. So we have x equals 1. Okay, except for the case, okay, a is 0. Okay, but a won't be 0. Why? Because we already have restriction on a. A must be bigger than 0 and a cannot be 1. Okay, otherwise, because let me tell you something. Because 0 to the power of 0 is undefined. Okay, so that means if y is 0, then x is 1. So this point must be 1, 0. Then, okay, 1, 0. So the first feature, the graph cuts the x-axis at 1, 0. Okay, the second feature, the graph never cuts the which axis. You can actually see the graph. The graph already cuts the x-axis, right? So that means the graph never cuts the y-axis. Okay, so I actually saw some people, they drew this kind of graph for me. They drew this graph. They cut the y-axis, okay? But let me just tell you, this is not correct, okay? Because the log graph never cuts the y-axis, okay? And we actually have a special name. This is wrong, okay? This is wrong, okay? Just be careful. We actually have a special name. for this line, let me write right here, okay, this line, y-axis, okay. Just remember when we learn the rational function, a line that a graph approaches but never intersects, what is its name? We call it asymptote, right? P-T-O-T-E, asymptote or asymptote. Okay, so this is actually the asymptote of this graph. Okay, so the graph never cuts the y-axis, and it lies on the right hand side of the y-axis, on the right hand side of the y-axis. So this is the second common features. The third common features is the graph has neither a maximum point, a minimum point, nor axis of symmetry. First, why it doesn't have a maximum point? The reason is clear, because you can actually see this graph is growing, right? It's growing, okay? It's like you're growing, although it doesn't skyrocket, but it's still growing slowly, okay? And it doesn't have a minimum point, okay? The same reason, it's still going down, okay? Nor axis of symmetry. That means this graph is not symmetrical. Okay, so these are the three common features for these two cases. Let me ask you now, do you know why the graph never cuts the y-axis? Okay, you know it never cuts the y-axis, right, from this graph. But why? Why it never cuts the y-axis? So this is interesting. Suppose if I say, okay, this graph, it cuts the y-axis at some point. Okay, so that means, let's say, okay, maybe the graph will intersect y-axis at this point. Okay, at this point. So, is that possible? How do we know that is impossible? We know this is impossible, right? But how can we know? Let's think, okay? If a point lies on y-axis, what properties does this point has? If a point lies on y-axis, that means the x-coordinate of this point must be 0, right? So this point must be 0 something, right? 0 something. If we can find the y-coordinate, then that means there is indeed one point there. Okay, so let's try. Suppose, let's say, okay, let's say when x is 0, okay, x is 0, so that means y equals log base a of 0. So what is the y value? We know this is impossible, right? Because the domain already tells us x must be greater than 0. But let us just, okay, we claim that is possible. That is possible. Then can we just change it to exponential form? We can write as a to the power of y equals 0, right? So a to the power of y equals 0. What is the value of y? Okay, suppose this a, okay, I don't use a, I use 2, okay, 2. 2 to the power of y is 0. Okay, is that possible? 2 to the power of y is 0. Let's say y is a negative number. Maybe y is negative 2. 2 to the power of negative 2. This will be 1/4, right? A quarter. So it's still a positive number. How about y is 0? Let's say y is 0. 2 to the power of 0 is still 1. Okay? Or if y is a positive number, let's say 2 to the power of 3. 3. Then that will be 8. What does that imply? That means no matter what the value of y is, 2 to the power of y must be a positive number. So we can't find a value of y in this case. So that means there's no such point. Okay, so this is wrong. We don't have this point. So that's why the graph never cuts the y-axis. Okay, so let's move on. Let's go to the second part, the differences. Okay, I'll just talk about the first one, the first case. Okay, because the second case is similar. Okay, so let's have a look. The first case, a is bigger than 1. Okay, the first differences. For x is in between 0 and 1, what is y? Okay, if x is in between 0 and 1, let me first write an interval. Let me write a vertical line, dotted line. Okay, if x is in between 0 and 1, that means x is here, right? X is in between 0 and 1. Okay, in this case, the graphs, you can see the graph. The graph will lies below the x-axis, right? What does that imply? That means the corresponding y value must be negative, right? All corresponding y value must be negative. So that means y is less than 0. Okay. How about second case? For x is bigger than 1, okay? This should be changed to 1, not 0. For x is bigger than 1, y, okay, so you can see the second case, okay? If x is bigger than 1, so this is the case when x is bigger than 1. Okay, you can see in this case, the graph will lie above the x-axis, right? So that means all the corresponding y value must be positive. So y is bigger than 0. Okay. The second one, as x increases, the value of y, okay, you can see the graph. The graph is growing, right? It's growing. Although it's not skyrocketing, but it's still growing. So that means as x increases, the value of y increases. Okay. If you don't believe me, let me draw a box for you. So suppose this, okay, this is x. Okay, so let's try to find the order pair. So this is x, this is y. Okay, so let's think together. Let's say when x is 1, what is y? Okay, let's say I give you this function. Y equals log base 2 of x. Okay, so when x is 1, what is y? Log base 2 of 1. 2 to the power of what is 1? 2 to the power of 0 is 1, right? How about when x is 2? 2 to the power of 1 is 2. How about 4? 2 to the power of 2 is 4. Okay, 8, 3, 16, 4, 32, 5. Okay, now we've got 6 pairs of 6 order pairs. Okay, now the third one. As x increases, the rate of increase of y becomes what? So how do we understand the rate of increase of y? This actually has the same meaning as how fast does y increase. Okay, so now we're asking, if x increase, how fast does y increase? Okay, let's look back to the last table that I drew. Okay, suppose, okay, this is x, right? Okay, suppose this is me. Okay, this is me. Now I walk 1 steps. I go from 1 to 2. I walk 1 steps. Okay, y will progress 1 unit, right? 0 to 1. Okay, now let me ask you, if I now keep walking, I walk 1 steps, will y progress 1 unit as well? No. This becomes more difficult. Now I need to walk 2 steps so that y will progress still 1 unit. Okay, how about second case? Can I walk 1 step so y will progress 1 unit? No, this time I need to walk 4 steps so that y progress 1 unit. What does that mean? It means things becomes more and more difficult. Okay, initially I walk 1 step, y progress 1 unit. Okay, but later on you can't do it again. You need to walk 2 steps so that y progress 1 unit. What does that imply? That means as x increase, the rate of increase of y will become smaller. Okay, so let's carry on to the last 3 boxes. Okay, the left hand side, okay, the first one, for x is in between 0 and 1, the value of a, the factor is the graph of y equals log base a of x. Okay. If x is in between 0 and 1, okay, we can have a look on the yellow graph, right? The 3 yellow graphs. 0.1, 0.25, 0.5, okay? Which one is the flattest one? I think it should be 0.1, right? This is flatter. Okay. So what does it mean? It means if a is smaller, the graph will be flatter. So we have the smaller the value of a, the flatter is the graph of y equals log base a of x. Okay, now the second part. For a bigger than, it should be 1, not 0. Okay. The value of a, the flatter is the graph of y equals log base a of x. Okay, so now we have got 3 graphs. Okay, no, yes, 3 graphs. Okay, we have the base is 2, the base is 4, and base is 10. Okay, let's have a look. Which graph is the flattest? Okay, I think it should be y equals log base 10 of x, right? So this one is the flatter one. So that means, okay, 10 is the biggest value, right? So that means the greater the value of a, the flatter is the graph of y equals y log base a of x. The next one, the graphs of y equals log base a of x and y equals log base 1 over a of x show reflectional symmetry with each other about the what? So let's have a look at the graph. Okay, I think it's clear, right? The axis of symmetry is the x-axis. Okay. The last one, the graphs of y equals a to the power of x and y equals log base a of x show reflectional symmetry with each other about the line what? Okay, so we have got 2 graphs there, right? One is green, one is orange. Okay, so which one is the axis of symmetry? It's clear. It is the line y equals x, right? However, when two functions they show reflectional symmetry about the line y equals x, these two functions they are very special. We have learned it in the function notes. Just remember, I've written it here. If two functions they are inverses of each other, they will show reflectional symmetry with each other about the line y equals x. What does that mean? That means, okay, now y equals a to the power of x and y equals log base a of x. They are inverses of each other. Can we prove that? How do we know if they are inverses of each other? Let me rewrite this function again. Y equals a to the power of x. How to find the inverse function? Do you still remember? The first step is let f of x is y, right? But now we have y already, so we don't need to do that. The second step, we make x the subject. How to make x the subject? This is exponential form, right? Can we get the log form? Power equals log base a of y. So now we make x the subject. The last step, what should we do? We swap x and y, right? You become me become you. So x becomes y, y becomes x. So y equals log base a of x. So you can see this function and this function, they're actually inverses. They're inverses of each other. Okay, and that's why they show reflectional symmetry about the line y equals x.